Last time we ended with this construct here, which we call HashSet, which allows us to store items exactly once and without recording the order in which we added items, which is already pretty useful for certain situations like the one down here, where maybe you want to check if there are any duplicates in a list, though there are other ways to do that, of course. And the trick about a hash set is that internally we are using the hash of a value to quickly find the position in a list of items where that item would be stored if it exists. Meaning adding items can take a bit because we have to really make sure that it doesn't exist already, which might include checking a couple of items that share the same hash code, but usually adding items is pretty quick. Checking if an item exists is also pretty quick. Removing items, same, pretty darn quick. Actually, we're talking about a constant lookup time, almost constant. Well, technically it does take a bit of extra time depending on how many items. Hash sets are incredibly quick. They do take some memory though. That's the trade-off here. That's where we left off. And today I'm looking at a different data structure that is surprisingly similar to a hash set, though we use it in a completely different way. And just like last time, let's actually drop this code. Don't need it anymore. And let's say I have a simple... No, let's do it... Yeah, fine, let's do it like this. String array, let's... simple array. We can access every single item in this array via its index. Array 0 would be equal to foo. Array 1 would be equal to bar. Index 2 doesn't exist. The array only has 1 and 0, 2 items. Now let's say I don't want to use an integer to reference that position. Let's say I want to associate a specific position in this array with a different value. So maybe instead of having an integer, I'm gonna use another string. So yeah, let's call it like this, but this one, for whatever reason, is all uppercase. Is it not? Did I switch the... There we go. Language settings. So we have 2 arrays now, and I want to check the lowercase version based on the uppercase version. Doesn't make much sense, I know. I can just convert if I need that value, but let's just pretend. This is something interesting. Well, actually, let's make this a bit more sensible. Let's say this is a mixed case situation, where could be any case, and this is what we look up. Yeah, makes a bit more sense, though it's still not the best example. I should have spent more time figuring out a good example. I want to use string index. Say we use foo, uppercase, as an index, and I want to find the position that it belongs to in the base array. I can go through the second array. What did I type? Int I equals 0, I less than a2.length plus I if array 2 a equals index Let's do like this. Then real equals I, and we can abort. And then we can check if real index is less than 0. That means we never found a match for index. We never found foo in array 2. And we can do something here. Let's just return for now, do nothing. But if we did find it, then we can check that value in array 2. Index. And get that back. Now imagine this whole thing would be arranged inside a data structure. I'm not bothering to do that because it really isn't that useful in of itself. But the basic idea is I have a value that leads me to find a different value. I have one string here that I can look up in one array that is associated with another string in a different array. Actually, we can make this a bit weirder. If we change this second one to integer, then our index would be integer. And let's make this 5, and this would be maybe minus 8,000, and this would be 5. This is a bit weird now, because the index we look up is an integer, but we use that integer to find the position in array 2, which is a different integer, but this time it's the real index in array that we want to look for. So we look for index 5, which is the value 5 in this array, which is at position 1, and then we go to array and look for the value at index 1 and return that. That would be the data structure we want. We can use any kind of value, an integer here or a string before, and it can reference any other type of value. A string, another integer, custom data type, whatever you want. And this can have some really useful properties. When we want to store just the position of a value. I mean, obviously the index as an integer is pretty efficient and easy, but in a larger program, well, let's say I want to have translations. I might have an original language that I want to store the values in and reference in. Let's just return this. So instead of foo and bar, maybe this is... These are the German words for 1 and 2. And 2. And I want to get the translation for eins, the German word for 1. By looking for the position in this first array, or this array 2 actually, I get an index that tells me the correct position in array that contains the English version of that word. And I can have easily other combinations of array and array 2 for different languages. That's one use case where we do actually want to link a value with another one in one single data structure. Of course, we could always just go ahead and make this, for example, a tuple, string A, string B. So and let's one and the next one two. Why is it? Please go to the next line. Oh yeah, we can remove this as well. But yeah, we could work like this as well. and ignore this. Just go through the array values like that. E dot A equals index. Then values I, B would give us the proper translation in that case. So instead of having two arrays, we can also have one array which just contains pairs of data. The same idea, just either we have two arrays which each contain one value per index, or we have one array which contains each combination of two values per index. But the basic idea is still the same. It's just a slightly different way of phrasing it, or presenting the data in the background. To access the data, however, we would still use our original value we want to look up and have to iterate through the entire list or entire array until we find the matching value, and then we have to return its counterpart from the other array or from the tuple in this case. And this type of data structure is so useful in so many different cases where you might not even think in the first place that it's useful. And sometimes because you're lazy. And there should actually be another way to do that, but you're too lazy for that, and screw performance, I guess. Well, it's so common that there is an optimized version of this, which involves hashes, of course. And this special data structure is called, well, depends on what language we're using, which exact implementation we have, but common phrasing is HashMap, as opposed to the HashSet. HashMaps would have two generics, so not just one generic like the HashSet, because we're not storing a single value, we store combinations of two values which can have entirely different data types. So we need two different generic parameters. And one is for the so-called key. That's the value we look for initially, and we use that key to get the value. And that's what the HashMap would look like as a class. And HashMaps are so incredibly similar to HashSets internally, though, that we can just rename this. TP. And make modifications to the HashSet to work as a hash map. To start with, we're gonna expand item. Currently we're storing only a single value per item, and that would be the equivalent of the key, because all the hashing, all the hash-based logic is all focused around the key. The value is only an afterthought. But we have to add it, of course, in here, and autocomplete already suggested the correct value, because sometimes it's correct. You have to always check what it's suggesting, though. It does a lot of things as well. Type for the key is the type for the key, and t-value, generic data type, is for value. So far so good. What did I click? I clicked something, let's ignore that. Let's make some modifications. First, contains. Well, this one can actually largely stay the same. We're just gonna rename a few things. We're not checking if it contains something, we need to specify that it contains a specific key. We could also make it contains value. But we have to now distinguish between, are we looking for the key or the value? Both are things you might want to check if they exist. And let's also rename this because it's a bit more generic. Or not as generic anymore, other way around, it's more specific. We're looking for a key. We're looking for an item in our hash map that contains this specific key. Okay, but otherwise contains, we can leave as is. Remove, very similar. Also just rename this to key, because everything is focused on the key. We always just care about the key, almost always, because all the logic only revolves around key. But we do have to make one change in remove, at least one. Remember this from last time? We have to clear up the old value in our hash set because of garbage collection. We have to make sure this value doesn't exist in our set anymore, so whoever gave it to us has, in theory, full control over if it is still remaining in memory or not. And because now we store two different values, one key and the actual value, we have to also free the value. And here autocomplete didn't quite get it right. Default. So we have to free the value as well, just like key. But apart from that, remove can actually stay as it is as well. Didn't really change much. Now add is a bit different. Well, not too different actually, because the logic for increasing the size, of course, stays exactly the same, and we still want to check if the value exists in the first place, because why should we add it if it exists? The first difference is, of course, we have to set the value. Items index to use dot value equals, that's the first part. We have to add a value in here as well. Value, and that should be renamed to key. Now we can add value as well. So that's number one. We have now two values or two arguments we have to provide. The key, which is the item in the hash set, and a value. All the logic is still focused around the key. We just have to finally add value as a payload, so to speak. But that includes a different topic now. In the hash set, the only information that mattered is, does the item exist or does it not exist? If it exists, we can abort and everything's fine. If it does exist, not exist, we can add it and it's fine. But now we don't have a single key anymore. We have also a value associated with it. And even though the key might exist, it might store a different value. So we might need to change the value of an existing item. We might need to change an existing item. So we cannot just abort up here. Just because we find the value doesn't mean we can abort. We might still need to update whatever it stores. So instead of doing contains key up here, we're gonna do this part manually. And we're gonna change a few things. So to start off, hash code. We need to generate that anyway, that's fine. We can keep that up there. And buckets index, we can also keep that in there. So we use the buckets index generated up here. We just move those two lines up. So before we only generated them in the end here. Now we generate them up here already because they need it anyway. We have to still pay attention to the bucket length though, for two reasons. Number one, this is where we check if the item exists. This is where we increase the size of the entire internal array, or both arrays actually. If we do find that we need to add the item, if it didn't exist already, so we don't just update its value, we have to add a new value. And that means potentially increasing the size of the entire array, which means this value is actually different. so bucket index might change. So in here, we actually have to update that value with the new bucket length, the new bucket size. Yep. Just to make sure that value is correct when we finally get down here. Next issue we might have with bucket length. This could be a 0. At least so far we initialize everything with 0 items, the 0 length array, which wasn't an issue before because the contains checks for there are no items. But once we have at least one item, buckets will not be 0 anymore, so this code would be fine. But the very first item we add to our structure, well, it will still find a bucket without any values in there, with length 0. And this code will not work. It's a modulo operation, not a division. But just like division, you cannot have modulo 0. That's not possible. That's an error. That would throw an exception. So we can only run this code if we actually have any items. Or if bucket length at least is greater than 0. But also if the bucket length is greater than 0, if the count is less than 1, if there are no items, we can also skip this part. Just like we did in the contains. So we have to do that as well. We still have to check the hash code, because we need that. Let's keep that in. But we can make the count is greater than 0. Only then do we actually check if the item exists. Not only then do we actually look in the bucket length. So that's fine. Of course, bucket index is now declared inside this scope and not available down here anymore. So we have to split this up and put that outside. So bucket index exists in the right scope, but now it might not be initialized correctly. That's why it's complaining now. Because we only assign a value if this is true or if this is true. And we have to give it a value for neither. So let's just give it a default value of -1. It's an invalid index, so nothing can really break, but it makes sure that our code can compile and work. But there's a bit more we can do now. In this case, where we find out the item exists, well, I mentioned that we don't want to just abort, because we do actually need to do something, unlike the case with the HashSet. We now have the exact position of the item this key would point to. And that means we can also go items i.value equals value. Yes, that's correct. Autocomplete. For once, we update the value. Now we have to make a decision. Our add before gave a boolean to determine if the item was new or not. So strictly speaking, with that logic, we would have to return false because we didn't add anything. But in the same time, we did change something, so we did add the value. So do we return a true? Do we return a false? That's a difficult question. And the surprising answer is neither. Well, maybe not quite so surprising if I tell you that there should be at least one more method that can add values. And this add method is specifically for new values only. So the case where we have the key already stored, we will not allow it to just overwrite stuff. So, and we're gonna do something crazy maybe, because we haven't done something this I'm tempted to say elaborate, but it's actually pretty basic system. We're gonna make this private, and we're gonna rename this method because it's not adding anything. It's let's just call it set, maybe set method. And this set method then has to distinguish between I'm adding a new value and there's no conflict, I'm not changing anything that existed before, or I'm updating a value where I override the existing value of a key I already have. For that I'm adding a boolean here, override. We're gonna use this method in a minute, just have patience. If we do override, let's put that up here. If we do override, then we can just override the value with our new value and return true, just to confirm that we did override something. We did store the value. We did set it. However, if override is false, if we do not want to override anything, then we need to instead return a false. Just to make clear that we did not set the value. And down here, we return a true. In the case we added a completely new value because we did add the value it is stored. So right now, this method is purely internal, it's private, so only our class can see it. We cannot access it directly, but it lets us somewhat efficiently add a new value, like before, and we can override an existing value, if we allow that. We can also tell the system to not allow overwriting values and just abort on this case. And actually we can swap this around, make the logic a bit simpler. No more brackets needed, it's simple return directly. We can override and do it like that. Now comes the public facing method. Public bool add. That's the method we can see for adding. It's only going to have these two arguments, the key and the value. And we can set key and value. And for adding, we do not want to override. If we add a value, we expect it to actually add it. We don't want to change anything that already is there. So we check the return value. If the return value is false, that means the value already existed. And if that already existed, we simply cause an exception. And specifically an argument exception. Let's give it a nice message. He already exists. Cannot overwrite. Let's do it like that. Name of E. And yeah, let's keep it like that. So argument exception is, what did I write here? Specifically for one of the arguments is unusable for whatever reason. For us, that is, the key already exists. We already stored a value with that key before, and we use the add method, which prevents us to change any existing values. We can only add information. We cannot remove information. And overwriting the old value would count as we remove the old data. Because of that, this bool also doesn't make any sense anymore, because it either succeeds or we get an exception. And this part only stores on a variable, so we can also just put it directly in here. Save a bit of space. Actually, I forgot the not. So now we have an add method that will internally call the set method without allowing overrides. So we can throw an exception if the key was already present. And we can offer a different method. It's called insert key t value value like that. And this one will just straight up use the set method key value true. And return a boolean depending on whether or not we successfully added or not. Which is always going to be true, so this doesn't actually make sense. Wait, what did I write here? Oh. Yeah, I should have switched logic. Okay, so right now we have the... I didn't pay attention, I'm sorry. I should have changed the logic. I knew something was weird when I added the argument exception in the add method. Okay, let's fix that. Let's take that as a learning opportunity. I made a mistake in my logic. The code is perfectly fine and works. It's just not very useful. Right now, the set method with an override equal to true will always return a true. It's the only outcome we can get from here. So this insert method will always return a true. Doesn't matter what happens. So that doesn't seem useful. What I actually want is the information whether or not I've added a new value or if it's just changing an existing value. That is useful. So the set method should return different booleans depending on if it's overwriting or adding. So let's keep adding as true and overwriting should be false. That of course means that this logic doesn't work anymore because, well, actually it does work technically. We can leave it like this. But the simpler method would be just remove the exception from here and put it in here. Let the set method cause the exception. Let it just happen. Like that. The add method still doesn't care about the return value because either it was added or it caused an exception, so we can leave it void. The insert method, however, can give a useful boolean back. So we cleaned up that mess. Good. And with that we can insert values, which always either overrides or adds a value. So it's the save option. Or we can use the add method, which ensures that only unique new values can be added, and we can't accidentally override existing ones. Now we also need a new method that's missing from the HashSet. Well, it's almost missing from the HashSet. We do have it in some form here in the contains key. We need to get the value. Contains key already reads information from a HashSet, because it tells us, does the key exist, yes or no, and that's the only information we store in there. But for the HashMap, we do need to get the actual value. We can actually copy this method and we can change this a bit, and let's call it getValue. And it will return t-value for a given key. Now let's ignore the case for count less than 1 for now. Just let's do the easy part. We still have to figure out the hashes, find the proper item, and have to return .value, like that. Actually, that wasn't necessary. So if we do it like this, the system will check the internal arrays for an item that matches our key and return the matching value. Very similar to our initial mockup code we had in the main. If that wasn't the case, if we didn't find the item, we have two options. We can either return a default, which we can also do up here, or we simply do it like the add method and throw an exception. As well, we can do this. Remember, exceptions are for exceptional circumstances. You are trying to do something that the computer cannot accomplish. You're trying to do something that the computer is not equipped to deal with. It doesn't know how to react. And right now we're trying to get a value for a key. But if that key is never stored anywhere, then the computer should not be able to fulfill that request and give us anything. Because technically, whatever the default is, could be null for reference types, or just a 0 or false, depending on whatever data type is. That could be also an intentional value we want to store. So if I want to store integers in our hash map, well, why should I not be able to store a 0? So this get value might return 0 for a key, and we do not know if that's the case because the key didn't exist, or because it did exist and just happened to be the default value 0. So this on its own is not a good design. It leaves too much open for interpretation by the programmer, and the computer should just complain about this. And we do that by throwing new... what do we do? Alright, we reuse an existing exception that is specifically for this case. Key not found exception. Cannot find key. Chill, no, let's not do that. Cannot find key. Good enough. Let's do it here, and we can do that down here. And the reason I do it in two places is for performance only. In theory, I could modify this code to just throw the exception down here. I would have to still generate the hash, even if that's not necessary, and we still have to protect this part in case bucket length is 0. And bucket index has to be something sensible, and would have to catch a lot of things in the code, and it's just easier to catch it up here and then a fallback down here. Either there are no items at all and we skip all this code, or we did have any items and we did perform all this code but still could not find it. Alternatively, let's duplicate this. We can use a type of method we already have seen before when talking about parsing, and that's try get value. Remember the try parse methods, where we have either the parsing methods like int.parse, or the try but tell me if it works or not, try parse. Same situation. The int.parse method might fail and we get an exception. Get value might fail, we get an exception. The try path will just return a boolean that tells us whether or not it worked, and the value will be in the out variable. Like that. And we're going to start by setting value to default. This time that is fine, however, because of the return value, we will always know if value, the value we actually return, is meant to be default because it's stored, or if it's just default because we didn't find anything. So because of the return value bool, we do know which of these two cases it is. We do not lose that information. It's fine to have it as default in this case. And if it's empty, we can just return false. We did not find it. If we did find it, return true and set value to an item value. And down here we can do return false again. So now we have two methods, depending on my circumstances, to read the value. If you're not certain if a key exists, you can use try_get_value. And if you're pretty sure that your hash map should contain the value and anything else would be an error, you just use get_value. In which case you get directly the value back, which makes it easier to program, and you get a proper exception already to deal with the unforeseen circumstances of something went wrong and your hash map didn't contain this value it should contain. By the way, you could, of course, at any point just use code to run contains key, and then only if contains key returns true, use get_value to read it. If you think about it, try_get_value is a combination of contains key and get_value. But the important bit is that try_get_value is a lot more efficient, because for contains key we have to run this code and then have to run it a second time for get_value. But try_get_value gives you all of that information while only running this code once. So, depending on your circumstances, one might be preferable over the other. In general, try_get_value is probably what you want. Okay, so we can add values, we can update values, we can check if they exist, we can remove them, and we can read them. In total, I think we have a fully functional hash map now, but didn't forget anything. How to use it? Well, let's make a new hash map, and let's use, just like before, the example of strings. Hash map. It's new hash map. That. And we can use hashmap.add, for example. Add translations again. Or we could use hashmap.insert. Also works for adding values. If I were to run hashmap again for add, like this would cause a fail because the key 1 already exists, so this would throw an exception. This would be fine and just override the existing value. But in any case, we can add and insert, we can remove something based on its key. Map.contains key. Can test if something exists, or we could just go for try_get_value. And check if the value exists, and if so, maybe output the value. So if I just run this code, it should not fail, and should probably add the counterpart. Like that. Doesn't exist, correct? Let's do 2. And the output is 2. So our hash map seems to work. Now, because we basically recreate some of the functionality of arrays with having an index and all, wouldn't it be nice to have some of that convenience as well? And specifically, I'm talking about the convenience of just using this. Making the syntax a bit easier. Or maybe like that. How do we make this code work? Well, we did talk about a certain feature already. The indexer. You can just create an indexer that returns a value, but instead of int index, like we did for the array list, I think, we can use t_key, key, and have that return the value by just running return get value key, like that, and set key combinations set. We're just gonna run insert key value. Keep in mind, this value is the standard keyword value for properties, for the set part of properties, not any variable. Like, I mean, it's a variable, but it's a predefined variable. This is the keyword value. This is not related to us using the concept of value in our item struct down here. Now, this is the interesting part that we should talk about. That's why I'm bringing this up. You see it's currently marked in red because this couldn't compile. And the error message complains about item already existing. And it refers specifically to our internal struct item. If we were to rename this, let's do item underscore, we don't get an error anymore. Everything is fine. But we reset. Having item internally is an issue. It clashes with this indexer. Even though it's just an indexer, why would this cause issues? This is just fluff. It's syntactic sugar. Like, having the option to write this out is just convenient. It's just less stuff to write, makes the code a bit shorter. And it can make the code look more uniform if you have different classes that all agree on using this feature. But internally, it has to translate that into some specific code still. And to do that, it needs, sometimes, depending on what you use, its own functions and item types and data types, and sometimes it even creates entire new classes. It depends on what kind of feature of the language you're using that makes your life easier, but the compilers work a bit harder. And in this case, well, it does need an internal item. And the ways around that is, well, to either do it like I did before, renaming our own struct, or you can rename the internally used item. We're not talking about how to do that yet, just leaving it out there. It is a possibility. You can tell the compiler in a specific way to use something other than item. But we're just going to use different name here because it's easy and it's purely internal data structure anyway, so it's not affecting anything on the outside. I should be able to run this code now and it should work just fine. Outputs 2. And there we have a hash map. Let's try something a bit more advanced. Yeah, let's do something fun here. You can stack different data types, so we can have a string as the key and a list of characters as its value. List character. This is entirely possible. It's no different than having an array of lists of characters. Just looks different. It's a hash map now. So instead of having individual indices, we have strings to act as positions inside a list of lists, kind of. So let's create hashmap.add. Well, let's use lowercase foo, and we add a new list. And we pre-fill this list with foo. So if I go for HashMap, try get value, foo, out, list char. Let's just use value. If try get value, then we can do something. But if it's not in there, we have the option to add let's char. So just to show off something, this kind of situation, at least to me, happens quite often. I have a simple data type like strings or integers or, well, generally very simple single value data types as a key, and something complex like my own custom classes, which might actually resolve in trees, or like here, like a list, or maybe an entirely new hash map. That could also happen, like a hash map that refers to hash maps. And in those cases, what often happens is I want to access the values inside my value, if that makes sense. So I have a data structure as a single value inside my larger data structure. And list actually, yes, do it like this. Let's say I have a specific sub data structure I need to access and work on that might or might not exist. What I want to do here, activity list equals to value, and I want to use list.add. Oh wait, like that. Do it like this. Extend the internal data structure. So I get the data structure of the list using a specific key, and now I want to change that internal data structure, which is contained in that larger data structure. Remember, list is a reference type, so this is actually just the address in the heap where our list is stored. So once I get that out of the hash map, I can just edit that, and what I'm adding here is added to the data structure in the heap, to our list in the heap. And our hash map still refers to that same address, so that doesn't change. I can just get the list out and change it, and the existing list inside the hash map is changed. I'm not copying the list out and have an entirely new list. I'm actually changing now the list that is already inside our hash map. But often I have the situation where I want to do something like this. I have a list, I want to add a value to that list, but that value might not exist yet. Try get value will get the value out if it exists, and we store it in list. And if that's not the case, we have to add it first. And actually, let's not do that in the else part. Let's do it like this either. I'm just gonna make a shortcut here because I want to speed things up a bit. What you usually do in that case is you just try get value. If that succeeds, we can actually use value directly. So once we run this line inside the if, this variable value exists inside this entire scope and we can use it directly. So if this returns true, this part is ignored and we can directly use value and add something to that. With the not, however, we make sure that if that was not the case, we can run this code, and what we can do is list char list. Actually, let's make it simpler. List new and that. So if that was not the case, value will be just the default. if we enter this scope, it means value will be the default value, which is null, because we set it to default on here. And so we override that with an actual newly created list, and then store that back into the hash map for the next time we run this code. But also value has now a proper list it points to, and so we can use that and add something. So just want to demonstrate, this is a pretty common construct where we will use the try-get method for hash maps. And by the way, while HashSet exists as a ready-to-use data structure, HashMap actually has a different name in C#. We call it dictionary. Though the methods are very, very similar. Purely coincidental, of course. But yeah, this code works the same for dictionaries as well. Let's rename this. And so this structure is quite common, at least for me. Like this specific style. If not try-get value, give a proper default value that you define yourself, and update the dictionary to contain that value for the next time. And then do something with that value. Like these 5 lines here, these 3 lines of actual code are common. At least to me. Yeah, and that's hash maps/dictionaries. And with that, I'm gonna end it early for today. I'm not too certain which topic I'm gonna tackle next, because I wanted to go a bit more into memory management and garbage collection, but I'm afraid that's not good enough for an entire episode, so we might actually start with multi-threading next time. Yay! Looking forward to that. But no matter what happens, your homework, try to create a dictionary, equivalent to the dictionary. You don't have to use a hash map technically, you don't have to create a hash-based system. For now, just try to create any data structure that maybe internally uses value tuples in an array or multiple arrays, the way I demonstrated in the very beginning inside the main method. Or you can try to recreate the dictionary like I did using the HashSet you were supposed to create for today's homework. And once you've done that, maybe play around a bit with dictionaries, things you can do, things you cannot do, get a feel for it. Get a bit crazy. Maybe make a dictionary inside a dictionary inside a dictionary. Oh, this, as far as usages are concerned, one thing that also happens, let's say I have a struct something, and I have int A and B. I don't want it to be private. Public. I just thought of it, and I think we can fit that in right now. So we can have a dictionary that has int as key and something as value. Dictionary. And let's say I have an array of something. New something equals 1, b equals 10. Why cannot let me type, please? That and like that. And now I want to go through the entire array and add them to the dictionary to group them up. Add .a something. So what I've done here, let's remove that, is use the dictionary to group an existing list of data based on one of its features. So if I know that I'm going to work with this data a lot, and I don't care about the order in which it is stored, I just care about some specific property in here, based on which I want to do some stuff, then I can just add them to a dictionary and use that specific property, in this case the field A, as the key. And using that, I can now just look for something that has 1 as its field. So grouping data is one use case where you might want to do this, or at least organizing in this case. Grouping would be a bit more interesting. This is where we have the aforementioned situation with a list of something. And this is where we would do the whole, if not, drag a value, something.a, out, something, oh, let's use value, not out something value. Oh yeah, sorry. Lists value. Something, then value equals something. We store it with the property A, and we can just value.add. I said add something. Okay. This is where we would reuse the structure from earlier. So even if a value appears twice now, so we have two somethings with property A equal to 1, it's not a problem. We just have a dictionary with two different keys. Key 1, which contains 2 values, and dictionary 378, which only exists once, with value -18 for B. Yeah. Another rather common use case for dictionaries, at least for me. If I need to organize some data, this is often something I do. At least on the assumption that this is not too large and I'm gonna reuse that same information a couple of times. Otherwise, there are probably better ways to group them up or organize the data in some different way. But for a small list of data or for something that you use quite a lot, this might be actually a better way to represent it. So instead of one linear list, organize it into groups and then handle it that way. Which brings us actually back to hash sets and hash maps internally, because imagine this being the hash value. For each hash value, we have a list of actual object instances which generate that exact hash value. So the circle closes. We use a dictionary which internally uses hashes to create a simple data structure that uses hashes, potentially. Okay, that might not make sense to you right now. I have it in my head right now. I think I want to try that. Create a dictionary by using a dictionary. That makes so little sense. I have to try it. Anyway. Have fun with dictionaries. See you next time.